Good morning, everyone. And if you are coming up from recording, good afternoon or good night, whichever. Today, or rather yesterday, we dove into trees and graphs. I didn't do too many problems. I'm so sorry. But I did do breadth first search and depth first search, which is super important. Now, the next chapter is bit manipulation. And I get asked literally 0 questions ever on bit manipulation. And it is a tough subject because it deals with ones and zeros, how to shift them, how to mask them, how to do all these things you can do with bits. Bits kind of make, code hard. We don't use them ever on the front end. There are some use cases for them that are very interesting, but I won't be going over it. And I've never fully studied the chapter or done many of the questions, and I've still gotten plenty of jobs over the years. Chapter 6 is math and logic puzzles. We will also be skipping these. Don't typically get many questions on them, which is great. Object-oriented design, yeah, that could be really good. If you're new to object-oriented design, check it out. I don't come across a lot of questions for that. Sometimes I do, especially back-end oriented jobs. Or basically anything that's not fully front-end. Front-end, we don't do too much object-oriented programming. It tends to run functional and reactive because of React. Thank you, React. So instead, we're going to go over chapter 8, recursion and dynamic programming. It's on page 130. This chapter is going to be one of the most toughest chapters you'll ever have to wrap your mind around. And I don't think I fully wrapped it around until the 3rd job cycle. The good news is that I'm typically only asked 2 or 3 recursion questions ever during an interview. And we're going to go over those today first. So this is going to be a really good video for you. If you're like, well, how do I do recursion? I'm just going to be like, just study these 3 questions. You'll probably be okay. Now, there is a way to solve recursion programs that I have developed over the years. I love it. However, it is highly complicated and it's for complicated questions. And I don't get asked complicated recursion questions often, or rather ever. Being able to know, here's the thing though, any recursion problem can be solved iteratively. And what does that mean? Well, recursive program is a function that calls itself to solve the problem. And it'll return once it's reached a base case. The most important thing is the base case. That's what stops the function from calling itself. You have to code it that way, or it'll go on forever. Iteratively is basically everything we've been doing up to this point, except for depth first search. That was recursive, right? Breadth first search was the iterative approach. Depth first search was more of a recursive approach. You can do depth first search iteratively. And one of the biggest hints is that, in recursion, a function call goes on a stack, right? A stack, it's a stack of function calls. They pop it off the stack. You push something new on, they pop that off, and they pop off the rest of them until you've called all the function calls. You can implement that as an actual stack and push and pop it in there to your heart's content, and it would become an iterative approach. It's not the only way, and we're going to see when I go over this chapter, we're going to see sort of what that means, sort of what that looks like, and you're going to see real quick that recursive thinking is different. So get ready. So I'm going to kind of read through the book. I'm not going to read the book. Frankly, I don't. I mostly just give my take on these sections. I recommend reading through the book. My favorite quote is this, though, and she says in here, in my experience coaching candidates, people typically have about 50% accuracy in their, this sounds like a recursive problem instinct. Use that instinct since that 50% is valuable, but don't be afraid to look at that problem in a different way, even if you initially thought it seemed recursive. There's also a 50% chance you were wrong. Not very comforting, is it? So what is she saying? She's saying, well, the problems in the back of chapter 8 are recursive. And you know that because I told you they were. It's the chapter on recursion. In the real world, you're going to get a problem and you might not know if it's recursive or not. It might just sound like it's recursive. And it could totally be wrong. I've made the call wrong before and I didn't get that job and it's not fun. And so it's tricky. It's tricky. I might show you, if we have time, I might show you the really advanced approach I take for this. It really helps me determine if a problem is recursive or not. It boils down to, can I represent the execution of my algorithm with a tree? And that is typically how I determine if it is going to be solved really well with recursion or not. It's a trick I've learned by kind of staring at this chapter and looking at, we're going to go into Fibonacci. She goes over what Fibonacci looks like from an execution standpoint, and it's a tree. And I was like, wait a minute, are they all trees? And they were. They all kind of have this tree execution flow, which makes sense, right? Because you execute one thing, you execute the function, it calls the function again, it execute it, there's another branch, executes again, another branch, another branch. And if, say, there are two of the same function call per, then it splits like a tree. There's a left node and a right node, and then those will have left nodes and right nodes, and those will have left nodes and right nodes. It looks like a tree. It's insane. It's absolutely insane. And then you just kind of have to figure out the base case from there, and then you're truly off to the races. It's really cool. I got too excited. Let's just dive into regular old recursive stuff and talk about how to approach these. And let's see. So she throws around this phrase, and you'll see this phrase a lot. And it's that recursive solutions are built off of solutions to sub problems. I found that to be wildly unhelpful, but that is kind of what it is, right? Say we're going to do Fibonacci soon. And Fibonacci, if you don't remember, it's 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. So the order is like 0, 1, 1, 2, 3, 5 for a Fibonacci sequence, and so on and so forth, right? The next number is 8, and then so on and so forth, right? Those can be broken into two subproblems. We're going to see how. And you're going to be like, there's no way I could have come up with that just by staring at it. And there is, but it is tough. It is very tough the first time around. In fact, just the last time I spiel on this, just go see multiple sources, multiple teaching sources of recursion to really help you with it. Maybe one of them will speak to you. Okay, now let's dive in. So it talks about the bottom-up approach, the top-down approach, the half and half approach. None of these approaches ever worked for me. I think the best section here was when she talks about recursive versus iterative solutions. And so why would you want an iterative solution over a recursive one? This is very important, and this will come up during an interview, so pay attention. Recursion is space inefficient because, like I said, each function call is popped onto that execution stack. And so you have an entire function call on a stack. So every time it's called, it's pushed on. That means every single call ends up on this stack. Before any function, typically, it doesn't stop putting things on this stack until it's reached the very bottom of the tree that it's building, right? And so that means all these functions being put on the stack, they don't get popped off until you've gone through the entire problem set, which is an O of n memory pressure. Yet to mention, if your recursion stack goes haywire enough on the browser, it's just going to say that there's too much on the stack, and it's gonna nuke you. And that's an issue, right? That's why we typically don't do recursion in the real world. It's just, for one, it's a little confusing to look at, but two, it's seriously, it can throw the browser off just by having a large enough stack. Is that called Stack Overflow? I frankly don't remember. But it kind of reminds me of it just from the wording. I don't think it is. You can Google that yourself, though. It doesn't matter. So a lot of the times, that means in an interview, you'll be asked a question, say, hey, flatten deeply nested arrays. And that is a major question. You should study that one. And you'll be like, okay, I could do that recursively, or one or the other. And so you do it recursively. And they're like, great job. Can you do it iteratively now? And you might be like, oh, I didn't practice that. And that's the cardinal sin. That's the bad way to approach learning recursion. Always, for the ones that I'm about to tell you, we're going to practice them at the end of this. Always figure out the iterative solution to that problem. We'll go over those problems at the end. One of them is flattening array. So there's also this take here on dynamic programming and memoization, which is an extremely important topic and does not stop when you are done with recursion. Whenever, like, caching and memoization are just really huge topics, and I'm almost amazed that they started here with it, but it's a big part of recursion because a lot of recursive functions need to be memoized. There's a lot of repeated work. Memoization, you can think of it like memorization, right? But instead of a computer memorizing, which it can't do, you're storing the result in, say, a hash map. And then whenever you have a function with the same arguments being called, you just pull the answer from the hash map instead of performing the actual calculation. Because if you're way up in the tree of this recursion execution stack, I just mixed data structures there. If you're way up in the execution stack and you haven't been popped yet, but you're sitting here waiting and you're about to do a whole host of other function stack calls to add to the stack. Well, if you already did them all, you don't want to create that branch, right? You don't want to create that second stack. You want it to, or it adds them to the same stack, whatever, but you don't want that to happen. You want to memoize it, so that is a big part of this. So memoization, basically, and you've seen it in React, there's a hook called use memo, and it's basically like, hey, as long as the arguments don't change, let's just return the same value. And that's basically what it is. You can do that to memoize your components. You can do that to memoize certain function calls in your hooks. And that's a very important topic. So it goes outside of just recursion, right? So, all right. So that's really important. So let's bring this all together. What does this look like? Let's go over Fibonacci with her in this book. I'm going to share my desktop. And we're going to use this tab and move some stuff out of the way. Oh, can't do that. Oh, like jellyfish. Cool. Okay. So we're going to create the Fibonacci algorithm. We're going to do it in two ways. One, we're going to do recursive, then we're going to do it with memoization, then we're going to do it iteratively. Don't skimp out on this. Fibonacci is asked during interviews. Okay, so it is stupid, but it's asked. So don't try to get away with not doing it. Fibonacci I for index, and like in. Let's do in. That might make more sense, right? So Fibonacci. What is the idea behind Fibonacci? I said it before, you have 0 plus 1 equals 1, right? And then you're like 1 plus 1 equals 2. And you're like 1 plus 2 equals 3. Cool. So how do we could probably think, I'm doing this iteratively. I'm showing you this iteratively. We could probably come up with a nice iterative version of this just by thinking through Fibonacci itself. However, with recursion, we take a different approach. And the first part is the base case, obviously, base case. The base case can change depending on implementations. I'm just going to follow the book in this, right? But the base case is what terminates the recursive function. So what is that going to look like? If n equals 0, return 0. If n equals 1, return 1. Cool. If that doesn't make sense, you can literally memorize it. But frankly, it'll start to make sense soon. All right, and it's going to make sense right about now. So we're going to return Fibonacci n minus 1 plus Fibonacci in -2. That's it. That's the whole shebang right there. And we're going to go up 5. And then we got 5. We're going to go up to 7. We got 13. Yay. So 7 iterations of Fibonacci is 13. We're going to go to 20. So, oh, look at that. This is cool. We're going to go to 30. And oh, that took a little while. Let's go to 50. And oh no, it's hung up. Right. So this is because we have repeated so many calls in this recursive function that it's now actually solving quite, I think 50 to the power of 2. What does that even look like? Let's do that here. So 50 the power of 2, 2500. No, that can't be right. Or is it 2 to the power of 50? One or the other. It's probably 2 to the power of 50. Huge number, right? You're never, you're never going to reach it. And I need to kill this. I need to kill this right now. There we go. And kill that tab. Okay, cool. It's a lot. All right, is it 2 to the power of 50? I don't know if that's the case. Huge number, right? If so, you know, it's definitely not 50 to the power of 2. That was stupid. So it is probably this 1.1 and then 50. 1, 2, 3, 4, 5, 6, 7. It is over a billion. Well over a billion, I think, which is crazy. It is. Why is that? That's because it's 2 to the n. It's 2 to the n runtime. That is O of 2 to the n. Yeah, isn't that insane? That's crazy. So if you have 50, it's 2 to the 50. So it's even here. An example of O to 2 to the n is recursive calculation of Fibonacci numbers. An algorithm whose growth doubles with each addition to the input set. The growth curve is exponential, starting off very shallow, then rising meteorically. That's why the first few were fine, is because it was, you know, it's not like an instant. It's not like you're instantly doing it. You know, if you're only doing 10, 2 to the 10 is not terrible, but it is a lot. So, oh no, is my browser now dead? It's not opening this anymore. I may have crashed it. Let me do a whole new window, see if that helps. Oh no, I bet you anything I'm just gonna have to reset my browser. I'm going to take care of that real quick. I'm going to have to pause recording. All right, we are back. I had to restart my browser to fix that. So, you know, if you ever let your recursion functions hang like that, excuse me, be prepared to turn stuff on and back off, turn stuff off and back on again. So how do we deal with this problem, right? It's seemingly impossible until you use memoization. So that is really good. So memoization is here for the rescue. How are we going to do it? So I'm going to, memoization is one of those things, might I say, that it could take a little time to remember how to do it. So practice it a whole bunch. This is my first time practicing in a while. So we're going to have to, you're just going to have to bear with me as I kind of copy from the book. Okay. So actually in the book on page 133, I mentioned this in one of my earlier videos where polymorphism is a thing in Java, but not JavaScript. In Java, if you have a function with different arguments, but the same name as each other, 2 different functions, same name, different arguments, it's valid. They're both basically different functions. And that's fine. So for us, we might want to say something different though. In JavaScript, we don't get that. We can't just have 2 functions with different arguments, but the same name. No, they're going to be the same. One of them is going to override the other. So we're going to say fib memoed. No, we're going to have this one be function fib. Actually, let's start with the memoized function first. So function memo fib in memo. Memo is going to be an array. So I'm going to give it a default. And then I'm going to say if in equals 0 or in equals 1, return n. That's just another way of doing the base case. Oh my God, there's so many ways to do a Fibonacci base case. So just keep that in mind. There's more than one way to do these things. So if memo at n, we want to, equals 0. We want this to be, in the book she does it if it equals 0. I don't like that. I want to say if not memo at n. If there isn't a memo at n, we're going to set it. We're going to be like memo at n equals memo fib n minus 1 memo plus memo fib n minus 2 memo, right? So you'll see what we did here. It was not that complicated. We said, we're not through yet either. We called the memo fib function, and you have to pass that memoization object down with it, in this case, an array, down with it. But the other parts were the same, n minus 1 plus n minus 2. You just kind of add this memo and you do a check if the memo has anything. If it doesn't have anything at the argument, say if there was an argument here or y, right? If not memo y, n, and I don't know, let's say it came into play like this, then then that's how that would work, because you're trying to memoize based off the arguments. If you have another argument, you want to memo based off that argument somehow too. And so that's how that works. So memo at typo. So memo at n now equals one of the function calls, right? And that's really good. That's what's gonna do. It's gonna help us out. Now I can show you why a little later, but that's how it works. So in other case, if it is there, we want to return memo at n. That's all there is to it. So yeah, that's it. Now let's call memo fib. Let's give it 8, 21. Oh, look at that. 12, 144. 49. Oh, ooh, look at that. 100. Maximum call stack size exceeded. Hey, there it is. There's the thing where I said, hey, if you go too big on your stack, it ain't gonna fly. There, look at how quickly it's computing these things and how big those numbers are. 2 to the, oh my God, you have fun counting that, right? 70 is over, I don't know what that number is, over a trillion, over a few trillion, whatever. So memoization makes it a lot more efficient. And why is that? I kind of gave a hint earlier. I think it's time that I go to, I think it's time I go to my iPad and show you the magic. Second. Okay, let me open up a new page here. All right, stop sharing there. All right, do this little song and dance. It's almost over. There we go. Okay, cool. So why did that happen? Why did that speed it up so gigantically? Well, let's take a look. Let me write out Fibonacci right here. I'm gonna basically, you got your base case, return fib. This is the important part I want to go over. N minus, so I'm not going to do it. Memwise plus fib n minus 2. These two things here, these are 2 function calls per function call. Crazy, right? So what does that look like though? What does that look like when we're building up the stack? Let's do it for Fibonacci of say 7. Now let's do it for Fibonacci of 5. Okay, so we got Fibonacci of 5. So what is this first one going to look like? We call fib of 5 here at the top. At the top. And it breaks out 2 functions. Here's the tree. I'm so excited. Fib of n minus 1. Fib of n minus 1. What is n minus 1? That's 5 minus 1. So this is going to be fib of 4. Right? That's fib of n minus 1. Then it's going to be plus fib of n minus 2. What is fib of n minus 2? That's 5 minus 2. That's 3. Okay. And then for each of these, we're going to do the same thing. So what's fib of n minus 1? That's 3. What's fib of n minus 2? That's 2. And so on and so forth. So fib of n minus 1, that's 2. Fib of n minus 2, fib of 1. And then we do it here again. Fib of 1, fib of 0. Interesting. These are our base cases, if you'll remember. If n equals 1 or n equals 0, stop. Or rather return 1 or return 0. And here we are again. We finish off there. Now it's fib of 2 over here. That's fib of 1. And we've got fib of 0. So those are also going to be our base case. And we're over here at fib of 3. We're just going to repeat some of the things we did because that's what we've been doing in the algorithm this whole time. Fib of 2, fib of 1. Base case, not base case. Okay, fib of 1, fib 0. Base case, base case. Look at that. We finally reached all the base cases. Now for 5, for the input of 5, that was easy enough to represent visually. And you see where we have repeated stuff. I'm going to do all the things that happened multiple times. Fib of 2, fib of 2, fib of 2. Cool. New color, yellow. Fib of 3, fib of 3. Cool. And then what else? We got, obviously, all of the base cases happened multiple times. Cool, whatever. There was a lot of repeated work. Now the base case is fine. You know, we can get rid of those very quickly, but we get rid of them the same way we get rid of these extra function calls. We don't need to call fib of 2 each time. We know the answer to fib of 2. It's always going to be fib of 1 plus fib of 0, which is 1 plus 0, which is 1. So if we can memoize that value, we could say memo at 2 equals 1, right? Nice. Now, what about 3? We could say memo at 3 equals what? Fib of 2 and fib of 1. Well, what's fib of 2? Fib of 2 is 1. Fib of 1 is also 1. So what is it going to be? It's going to be 2. Look at that. We can keep going. Memo at 4 equals, what is it? What does it equal? Pause right now. See if you can find out. I'll give you a hint. We're already showing it right here. So you have the executions here, and we've already memoized those values here. It's 3, right? So now every time we see fib of 4, right, maybe that's going to be multiple times, especially if this goes up to like fib of 50. Then we have fib of 4 memoized. Boom, all of this disappears. All of these executions disappear. They're gone. We already have fib of 3 as well. We don't need any of these. Oh, you know what we could even do then? We could memoize fib of 5. What's the memo at 5? It's 4 plus fib of 3. It's 5. There you go. You don't need to do any of it anymore. You could just return the number if it's 5, right? Easy. Well, not easy. It's kind of weird at first, but that's how it works. That's exactly how it works. That's how memoization saves it. So now when we call this, we're going to say fib of 5 equals 5. Boom. And we didn't do any of this tree nonsense. We didn't do any of these execution calls. And so that's why memoization is so powerful, because you can dodge doing all that work. OCD, I've missed a few little spots here. There we go. And yeah, so that is the power of memoization. You can return something immediately. It's just a hash map too. It's just a key value pair, which is really powerful, really, really powerful. So that's the magic of memoization, and that's how this is the biggest hint towards, you know, our stuff. Our recursion algorithms are trees. They execute as trees. And so if you can figure out a way to model your problem as a tree, it's probably a recursive problem, or it can be. It doesn't have to be. So that's really fun, right? That's really powerful stuff there. It took me years to figure that out. And it might not even make much sense yet. And it probably won't by the end of this video because we're not really going to cover it. So what's the second part? Well, now we need to do Fibonacci iteratively. Yikes, right? So iteratively means without recursion. How do we do that without the function calling itself again and again? Because we want to avoid the maximum call stack size exceeded problem. What was that number? We're going to do this. We're going to say max call stack equals this. It's probably less than that, frankly, but I don't care. Let's say, okay, so I once again, I'm going to look in the book for this because I need to practice doing it iteratively. It's really tough. Actually, you know, let's treat this as a practice interview question. Yeah. You know what? We're going to take this time to dive into practice interview questions. We are now transitioning. And for that, I actually have been changing the recordings for it. So I'm going to do that real quick. And I'll see you in the next video.